¿Me escucha? ¿Me está escuchando? Bien. Okay, good morning, everyone. We started with this session. All the sessions in this opportunity are online. The order that we want to use is that I sent some minutes ago by messenger. And the first presentation is given by Belén Sánchez Santero. When you want, you can start it, please. Can you listen to me, Belén? Okay. Can you listen to me?
Yes, we can. Yes.
Okay, thank you. And then we started this session. In the first talk, we have the presentation given by Belén Sánchez Santero. The title is on the IoT architecture for real-time monitoring and control of offshore wind turbine using multi-thread low-cost controllers. When you want, you can start it. Remember, you have maximum 15 minutes. It's better around 12 minutes to give some minutes to make question, if possible, please.
Okay, perfect. Start now. Good morning. My name is
Sorry, Carlos, but I think you should mute your. Yes, exactly. Thanks.
Okay. We are presenting our work on IoT architecture for real-time monitoring and control of offshore wind turbines using multi-threaded low-cost microcontrollers. The presentation will begin with an overview of the context and motivation behind our work. We will then outline the system architecture and software implementation. Next, we will present use cases that illustrate the system behavior in practice. And finally, we will conclude with our findings and suggestions for future developments. In recent years, offshore wind energy has demonstrated annual growth rates of nearly 30% over the decade, driven by European investment and rapid technological advancement. Offshore wind farms benefit from stronger and more consistent wind patterns, resulting in higher efficiency than onshore installation. As you can see in the chart, installed capacity has increased consistently each year, and this trend is expected to continue. The European Union aims to install 200 gigawatts of new wind power capacity by the year 2030, with offshore energy playing a key role in this expansion. This strategic focus reflects European Union's commitment to reduce the dependence on fossil fuels and meeting its climate objectives. One of the most promising innovations in offshore wind energy is the floating turbines. These systems allow installation in deeper waters, up to 1,000 meters, opening access to previously unreachable sites. They also help minimize environmental impact and avoid interference with coastal regions. However, floating turbines also present several challenges, such as extreme marine conditions, increased control complexity, and elevated installation and maintenance costs. In order to keep developing floating offshore wind energy, it is essential to implement innovative control strategies that can handle the dynamic and unpredictable marine environment while ensuring structural integrity and system efficiency. This requires safe, scalable prototypes to test advanced control algorithms and easy-to-use interfaces for real-time monitoring and remote control. The goal of this work is to develop a low-cost system for monitoring and controlling offshore floating wind turbines.
Thank you, Valen. Our system architecture is structured in 3 core layers. The first, a physical prototype made of several components, such as a brushless motor that acts as the generator, a pitch actuator which adjusts the blade angle, a load actuator made of a relay system that applies varying electrical resistance to the motor, and an inertial measurement unit, MIN. It's also equipped with a dual-core ESP32 microcontroller, which is responsible for managing the local control loop, and a MATLAB-based graphical user interface connected to a ThinkSpeed cloud to enable remote monitoring and command execution. These components work together to replicate and manage the behavior of a floating wind turbine in real-time conditions. The ESP32 microcontroller runs 2 concurrent threads using the FreeRTOS real-time operating system. The control thread, which governs sensors and actuators and performs 1 iteration per second to keep a consistent control cycle with no gaps or interruptions, and the communication thread, which manages data exchange with the ThinkSpeed platform and uploads turbine states into JSON batches. These threads interact through a first-in, first-out message queue, one for transmitting turbine states and another for receiving control commands. This ensures consistency and reliability in the system's real-time performance. Here, the diagram shows the 2 threads running on the ESP32. The control thread receives commands, runs 1 iteration of the algorithm, and then reads the turbine state and sends the state to the communication thread. Meanwhile, the communication thread reads new commands from the cloud, sends them to the control, collects states, and uploads them back to the cloud. This design ensures real-time performance while keeping the control logic isolated and secure. The state queue transmits data at 1-second intervals from the control thread to the communication thread. Each message includes a timestamp, pitch angle, load setting, revolutions per minute, and the EMU readings. If the queue reaches capacity, the oldest entries are discarded to prevent overflow. The command queue stores only the latest instruction, including the desired operation mode, pitch angle, load value, or an emergency stop flag, which was exclusively designed for this prototype. This design ensures that the system always executes the most recent command received.
We developed the user interface in MATLAB using Model View Controller architectural pattern. The model stores turbine data and manages cloud communication. The view displays real-time system information and provides interactive controls. And the controller coordinates actions between the model and the view, including periodic data refresh. This modular approach enables system maintainability and scalability across different turbine types. The farm view displays a map with turbine location and overall status. It includes a side panel to switch turbines and panels showing project details and real-time power output. The turbine view offers detailed data for an individual turbine, including wind and wave condition, temperature, and metrics like pitch angle, load, RPM, and power. Users can switch between automatic or manual mode, adjust pitch or load, and activate the emergency stop. Also, several graphs enable continuous performance monitoring.
Let us examine the system performance in automatic mode. At startup, blades are stationary while sensor and connections initialize. In low wind, the pitch is set to 45 degrees to overcome friction. As wind increases, the next slide. As wind increases, revolution rises, and the controller maintains stability via pitch and load regulation. If wind speed surpasses the safe threshold, an emergency stop is triggered to protect the system and the structure.
In manual mode, users can directly test how the turbine responds to specific commands. In the first example, the load is manually increased. As we can see on the right, this causes a small drop in revolutions, but increases power output. This simulates a rising energy demand from the generator. In the second example, the pitch angle is manually reduced to 0 degrees, which is close to its optimal value. This results in a sharp rise of revolutions over 200% and higher power output. However, the system detects that the revolution has gone out of safe range, triggering a risk alert. To prevent damage, the user then triggers an emergency stop. The system responds by applying protective values for pitch and load. As we can see, the alert clears and the turbine returns to a safe state.
To conclude, we have developed a low-cost modular architecture for offshore wind turbine monitoring and control, based on a multi-thread ESP32 microcontroller, which was key during this development. The system runs concurrent control and communication processes with FIFO message queues, ensuring real-time performance and safety. The MATLAB interface and TeamSpeak integration allow remote monitoring and control. Its design supports rapid prototyping and adaptation to new turbines or control algorithms. In future work, we plan to enhance signal processing with Kalman and Fourier filters and explore the integration with AI-based control strategies. Thank you for your attention. We will be welcoming any questions you may have.
Okay, thank you very much for your presentation. If someone has some question here in the room, I have a small question. Is in relation with the dynamic of the floating platform, and how this moving platform could affect to the control system for your system that you are designing using ESP32.
Yeah, the data that is handled right now in our prototype, indeed the inertial measurement unit is prepared to read data and to send it to the cloud, but the algorithm is not prepared to handle the data in of PID control. So it will be a feature for future developments, I think. The thing that is implemented right now is the wind parameter in the sea. The floating variable is not taken into account.
Okay, thank you very much. We have no more time for more question. And then we follow with the next paper. That is,
Thank you.
thank you much. The next paper is presented by Milan Soltani. That is titled Evolution of the Sensibility of Measurement Circuits for Corona Discharge Detection. Can you share your presentation, please?
Hello, everyone. Can you hear me?
Yes, we can listen to you.
Okay, I share my presentation. Okay, is it fine?
Yes, it's fine. You can start.
Dear ladies and gentlemen, thank you so much for joining my presentation for my paper, which was on evaluation of the sensitivity of measuring circuits for corona discharges detection. Before starting our presentation on the calibration circuits and the calibration of PD measuring systems, we have to define some fundamental subjects on partial discharge studies. First of all, what is partial discharges? Partial discharges play a major role in the degradation of the insulation in high voltage equipment. Partial discharge occurs when localized electrical breakdowns occur in the presence of a high electric field near an insulator. One of the important things subjects defined in the partial discharges is the apparent charge. Apparent charge, according to the IEC 60270 standard, apparent charge of a PD pulse is that the charge expressed in picocoulomb that, if injected between the two terminals of the device under test, would produce the same reading on the measuring instrument as that produced by the PD pulse. Since the actual charge involved in the discharge region or physical charge cannot be measured directly because the PD source is inaccessible, the apparent charge is measured instead. One of the important PD pulses, partial discharges, is the corona discharge. While the PD pulses can occur in insulation systems based on solid, liquid, or gaseous materials, when the PD occurs within a gaseous insulation such as atmospheric air, this type of discharge is typically known as corona. Corona typically occurs at sharp edges or points because of the high density of the electric air. As you can see in these pictures, the pictures are taken by us in the Amber laboratory of the UPC University. Here you can see a corona discharge in a sphere, and here you can see a corona glow on the DC mode. So all the photos you see in the presentation are taken by our laboratories. A critical aspect of the PD measurement is the calibration of the measurement system. Calibration results in a scale factor K that is used to convert the measured signal to the apparent charge. But before initiating the partial discharge calibration process, it is essential to ensure that our pulse generators are periodically calibrated using the procedures approved by the standards. The conventional approach actually to calibrate a PD calibrator is to inject a known charge and determine it by the numerically integrating the current flowing through a resistor placed between the calibrator output and the ground. As it can be seen in this photo here, The charge from the PD calibrator is injected into a resistor connected in parallel with the high impedance output of the digitizer, which here we use the oscilloscope as our digitizer. And the current flowing through the resistor can be determined by dividing the measured voltage by the value R of the resistor. The charge of the pulse can then be obtained by numerically integrating the current as this relation. And here we can see a PD pulse generated by a PD calibrator, which is this duration is the duration of the pulse, the time duration of the pulse. And by integrating this pulse through the time, we can acquire the charge of the pulse. After calibrating the PD calibrator, we have to calibrate our circuit. The calibration procedure involves injecting a pulse of a known charge between the two terminals of the device under test using a PD pulse generator and measuring the resulting charge at the measurement system. When performing the PD measurements, it is also important to know the background noise level, as it can greatly affect the sensitivity of the measurement. The background noise level can be characterized by the signal to noise ratio. Here, the URMS PD pulse is the RMS value of the voltage of our PD pulse, and the URMS of the noise is the RMS value of the voltage of the noise. And by dividing them, we can acquire the signal to noise ratio. Here we can see the 5 measurement circuits that we used to evaluate for our calibration. In the first circuit, a measuring impedance, or sometimes it is called the quadrupole, is in series with the coupling capacitor, and they both are in parallel with our device under test. In the second circuit, we have removed the quadrupole or the measuring impedance and put an HFCT on the side of our device under test. In the third circuit, we have the HFCT with the quadrupole and the coupling capacitor in parallel with our device under test. In the fourth circuit, we again removed the measuring impedance and put the HFCT on the side in series with the capacitor. And in our last circuit, we removed the HFCT and we put our measuring impedance in series with the device under test, and the coupling capacitor is in parallel with the whole device under test and the measuring impedance. For our experimental setup, we have used a Phoenix 50 Hz AC generator with 2 outputs. We used this source to generate the variable high voltage, and to minimize the noise level, 2 filters were used. One of them was on the low voltage side of the generator, which was a single phase filter produced by the TE connectivity. And another one was a high voltage side filter, which consists of 32 turns wound on a TDK Electronics epoxy N30 ferrite toroidal core, which and the total inductance of this filter was 5.1 millihenry. A Tekim PD generator was used during the calibration phase of the experiment, and also a CLP 542 measuring impedance. You can see the measuring impedance here. From the Omicron was used during our test, and an MCT high frequency current transformer, or HFCT, made by the Omicron was used, and also a Tektronix oscilloscope with frequency range of 200 megahertz here, and the sampling rate of 2.5 gigasamples per second. We used that. And for our test object here, we used a sphere to plane configuration, which is used widely in the high voltage. The diameter of the sphere is 14.5 millimeters, which was pointed 100 millimeters above a grounded plane. Here you can see the result that we got from calibrating of our pulse generator. As you can see, we did it for the 4 charge levels, 170, 50, and 30 picocoulombs. As you can see here, for example, when we inject 100 picocoulombs, we don't get 100 picocoulombs exactly by the PD calibrator, and we get around 95 picocoulombs. All these results are acquired for 30 samples. So for each charge level, we have got 30 samples, and by calculating the the average charge of those 30 samples, we have acquired these results. So during our calibration, we have to consider that when, for example, we set our PD calibrator on 100 picocoulombs, it doesn't inject 100 picocoulombs. It injects around 95 picocoulombs, or when we set it on 70 picocoulombs, it injects around 66 picocoulombs. And the sigma here is the standard deviation of the 30 samples acquired for each charge level. Here, we can see the results of the calibration for each circuit. As you can see, for the first circuit, which is the quadrupole in series with the coupling capacitor, we have a high signal-to-noise ratio, and also the calibration coefficient is 0.42 for 95 picocoulombs. For 66 picocoulombs, also it should not change too much according to the standard. For the different charge levels, uh, the calibration coefficient should differ at most 5% from the average value. So as you can see, the values of the calibration coefficient are near to each other. And as we decrease the charge, the injected charge, the signal to noise ratio is decreased because the amplitude of the pulse that we inject is decreased. For the second circuit, which is the HFCT on the side of our devices, you can see the signal to noise ratio is decreased, and also the coefficient, the K coefficient, is decreased too much if we want to compare it with the previous case. For the third circuit, which is the HFCT in series with the coupling capacitor, the calibration coefficient has increased a little bit here, but the signal to noise ratio has decreased. Also for our fourth circuit, as you can see here, the signal to noise ratio and the calibration factor are not too much, but the point is for the last circuit, which is the measuring impedance in series with the test object, we have the highest signal to noise ratio, and also the calibration factor is increased compared to the cases that we had the HFCT. So what we conclude is that the measurement circuit in which the measuring impedance is in series with the test object is the one with the higher signal to noise ratio and the sensitivity. But there is a point here that this system can be dangerous for our measuring systems, for example, for the quadrupole or for the oscilloscope, because if we have unwanted discharges or breakdowns, as the breakdown that you can see here, it can actually put in risk our measuring devices. So circuit number 1 offers better protection for the measurement devices against accidental discharges because the measuring impedance is in series with the coupling capacitor and not in series with our test object. And also, the HFCT produces the most accurate results when connected in series with the both coupling capacitor and the measuring impedance. It is the most sensitive.
Are you here? Milad Saltani, is you here? Looks like he lost the connection just in the last minute. Then we follow with the next presentation with Xavier Delgado Sanchez with the article titled Stability Analysis of Grid Following Converters in Power System Depending on Grid Stiffness.
Hi, can you hear me?
Yes, perfect.
Okay, I'm going to share my screen.
Go ahead.
Okay. Can you see the whole screen?
I can see your PowerPoint file, but I cannot see the presentation.
Okay.
Maybe
Let-
do you have the two screens or something?
Yes, let me. Okay. I think now you can see it. Okay.
Now it's perfect. Yes. Go ahead.
Okay. Hello, I'm Silvia Delgado Sanchez. I'm going to present my paper titled Stability Analysis of Following Converters in Power Systems Depending on Grid Stiffness. Now. This is the index I'm going to follow, and I'm going to start with an introduction to start defining some interesting terms. First, it is well known that our electrical energy sector is transitioning from carbon-based generation to clean generation with wind, solar, and hydroelectric resources. The former generation uses synchronous generators to connect to our grid, but clean generation uses instead power electronic converters. These two devices differentiate, have different properties, and one of the main ones is that power electronic converters lack inertia, which stabilizes the frequency in the short term when contingencies take place. So there's a need to study the integration of these devices in our electric grid. Two main control strategies are implemented nowadays in power converters: grid following control and grid forming control. The one that we are going to study in this paper is grid following, and I'm going to use the letters GFL to abbreviate. The aim of this paper is to demonstrate that the integration of grid following converters in weak grid results in dynamic instability when they are connected to weak grids. And to do so, I have developed 4 experiments. The first one being an analyzing of the converter's passivity. The second one performing a voltage dip test. After plotting the eigenvalues of the whole system, and finally analyzing the well-known impedance stability analysis method. Before introducing these experiments, I'm going to define briefly the grid following converters. Their control architecture is the one you can see in the slide, and they use a phase lock loop to synchronize to the grid. The PLL measures the grid voltage and obtains its angle to place the DQ reference axis, the internal ones, and they do so by setting the Q component of the voltage to 0 thanks to a proportional integral regulator. You can see also in the screen the characteristic current control loop of grid following converters. As I have said, grid following control produces, it has been said that they produce grid instability when they are connected to weak grids. Weak grids are the ones that have a large impedance or short circuit ratio. And in these cases, if this happens, a perturbation in the grid current significantly impacts the voltage, and then affects the PLL, which results in the problems of stability. So this stability is going to be analyzed in the frequency domain with the two methodology points I have here in the index. First, I'm going to define the impedance stability analysis, which consists in dividing any power system into subsystems. The first one being the Norton equivalent of the converter or the generator, and the other subsystem is reducing the rest of the grid to its Thevenin equivalent. If you calculate the voltage at the point of common coupling, which is the point where you analyze both impedances, the equation in the slide appears, and the system would be stable if the denominator doesn't equal to 1, or it can be said that if it satisfies the generalized Nyquist criterion, it will be stable. The generalized Nyquist criterion, why? Because the matrices of the impedances are squared, because you analyze them by injecting a DQ current and you obtain the measured DQ voltage. This is the DQ reference frame, and you can obtain the matrix in the modified sequence frame by applying the equations that appear in the screen. The other method, as I have said, is checking the passivity of the converter. How do you, a converter is non-passive if its conductance is negative. So in that case, the converter could jeopardize the stability of the system, but only if it matches the resonance of the grid. So it doesn't directly say which frequencies are unstable. You have to check with the resonances of the grid. There are two ways of analyzing the passivity of a converter. The first one is straightforward and is checking the impedance, the phase impedance, and if it lies between plus minus 90 degrees, the conductance is positive, so the converter could be passive. And the second is verifying that the eigenvalues of the sum of the DQ admittance plus its Hermitian transpose are positive, then you would have a passive converter. Here in the example, the purple eigenvalue is non-negative at some frequency range, so in that region it could be non-passive. The model implemented to analyze this is the same one as in the other slide, the grid following converter, and it is connected to a grid that is implemented as a voltage source behind a complex impedance, both with subscript 1 to note them. And how do we model the levels of stiffness? By varying directly the inductance. If it's there's a high inductance, then there will be low STR and then the weaker the grid. Both models are implemented into the MATLAB and Simulink environment to develop the experiments I'm going to explain. For the results, the data used is the one you can see in the screen. The power base for both the converter and the grid is the same, but the program can differentiate from both if the converter has a different one. And also the levels of stiffness are implemented in the impedance, as I have mentioned, and there are three cases from the strongest grid to the weaker grid. First, the passivity of the grid following converter is checked by the second method I explained before, verifying the equation you can see in the screen. And the results here are slightly different from the paper because I saw a slight error, but I have the conclusions and results are the same. So in the synchronous region, we have negative passivity values in the first one that is calculated, and low negative values in the subsynchronous region, sorry. This means that the higher the negative eigenvalue, the more concern we have to have because it could jeopardize the stability. After a voltage dip test is performed, here you can see the real reactive power and the voltage after applying a voltage dip to 0.8 per unit during 0.5 seconds, after which the voltage recovers its initial value. And as the grid gets weaker, the more oscillatory response we have. Even after recovering the voltage, the weakest grid has a loss of synchronism. We can see also the eigenvalues of the whole system. I have plotted them here. And also as the grid gets weaker, the closer the eigenvalues get to the imaginary axis, so the less damped and more oscillatory response we are going to have. Finally, the grid and converter impedance stability analysis is applied. And I remember that we have to check the ratio between the grid impedance and the converter impedance. And to do so, I'm not going to use the Nyquist plot, I'm going to use the bold plots. And here you can see they are slightly different again from the changes after the submission, but they have the same conclusions. The weaker the grid, the closer both curves get So there are intersections that have to be studied. And here you see that in the weakest grid, they are in the synchronous range. And also I added another test of another even weaker grid. And you can see that there are also 4 additional intersection points in the supersynchronous region. Finally, checking the phase margin in intersection points will precisely determine which frequencies lead to instabilities, but this shows a clear pattern. Finally, in the conclusions, we can see that the statement of the objectives is verified. The weaker the grid connected to a grid following, the more instabilities show. First, the converter's passivity detailed the range of frequencies which could lead to instabilities prior to any other simulation. And the frequency domain impedance shows a clear pattern of the system stability as the grid gets weaker. Finally, as future work, it can be studied, these stability methods in more complex grid with multiple grid following converters to study interactions between them, and also implement this with grid forming converters as they are getting more interest in the scientific community. Thank you.
Thank you very much for your presentation. Someone has some questions in the room? Yes. Yes. Try to speak.
Okay.
Maxim.
Thank you for the presentation. I wanted to ask if you can comment on how realistic the solid weak grids are, in your opinion, or they're representative of some weak that you're aware of, some grid that you're aware of.
I didn't hear properly, sorry.
The question is how realistic the grids that you have studied are, weak grids.
Can you expect if you walk up to the front, this is microphone is right there, we can look at the
So the grid implemented is just a voltage source behind an impedance, and this is the simplest case. So another future work is using more complex grid and studying the interaction between other converters with grid following and everything that comes with that. But this is the simplest grid.
Thank you. I'm gonna try to repeat. Can you hear me?
Yes.
Okay. The question is, you showed different values of inductances for the grids that you tested. And the question is if it's based on grids that you know or how realistic these values are.
No, these values are just for simulating the increase of an inductance, and they are based on they are an impedance behind a voltage source. For more realistic values, you should take from the cases that you have online and they are validated to have more realistic results. But this is for having a clear vision of the pattern that it has.
Okay, thank you.
Thank you.
Thank you very much, Silvia. Maybe we have 1 minute for some question more. No more? Okay. Then we follow with the next presentation. It's the last one. Presentation is given by Fernando Herrera or Matilde is here. Matilde Santos, can you listen to me? Or Fernando Herrera? Looks like they are not here at the moment. Matilde Santos told me that Fernando will be the speaker, but it's not in this moment. You have some messenger here or something? Caroline.
Yes, I'm here.
Okay, Carolina is the paper. The first one is. Okay, then let's go for the presentation given by Carolina Martin. The paper is real-time optimization based in real power control strategy for the Lanzarote Fuerteventura power system, a comparative analysis. When you want, you can start it.
Okay, so can you see the full screen mode?
Yes, I can see.
Okay, so hello everyone. First of all, I would like to thank you all for attending this presentation. My name is Carolina Martin, and I'm a member of the Power Systems Control Research Group at ICREPQ. Today, I am honored to present this recent work, which I have developed together with my colleagues Francisco, Santiago, Jaime, and Jose Luis. Okay, so let's start with the introduction, presenting the motivation for our work. As you may be aware, the increasing integration of renewable energy, which is intermittent and distributed by nature, is creating major challenges for power system operation. At the same time, greater interconnection and monitoring of the grid allow for more advanced reactive power control strategies to address these issues. Among these, new strategies based on centralized control are being proposed, such as those based on optimal power flow. However, these approaches must be tested under realistic conditions, and this is why real time simulation and hardware in the loop tools have become essential. So, in this context, this paper has two objectives. First, it aims to develop a real time optimization based strategy for reactive power management that focuses on reducing costs and ensuring secure operation. And second, it aims to validate this strategy using RTO Lab, a real time hardware in the loop simulation platform specifically developed for this application. Okay, so let's now present the control strategy in general terms, highlighting its main features. As shown, this control strategy is designed to be integrated into the current operation of power systems, where active power set points for dispatchable generators are typically determined by market clearing mechanisms or unit commitment results, usually scheduled 1 day ahead. So the proposed strategy takes these scheduled set points along with the most up-to-date forecast for renewable generation and load and executes in real time and at predefined intervals an optimization algorithm that computes the optimal reactive power sharing among the power plants in the system. That is the voltage or reactive power set points. This process is carried out periodically and in real time, allowing the incorporation of the most recent forecasts and therefore leading to more optimal results. Okay, so once we have presented the strategy, let's focus on the optimization algorithm. On the slide, you can see the complete optimization problem, which is based on a variant of the optimal power flow formulation. So let's begin by analyzing the objective function. As you can see, this objective function is formulated to minimize system losses in power lines, represented by the term P loss, you can see on the slide, as well as redispatch cost. Active power redispatch is required to ensure power balance in the system since the transmission system model is usually not considered during the power plant schedule performed the day before, and losses are not considered. Okay, so continuing with the constraints, these have been formulated to account for the technical limits of the grid and the generators. Therefore, the first two equations represent the active and reactive power balance at all the buses in the system. The third constraint defines the updated active power set points for the dispatchable units resulting from the redispatch process. The fourth and fifth equations impose limits on the active and reactive power output for the generators. Then we have the voltage limits at the buses and the operating limits in the power lines, which have been considered by calculating their current and imposing the maximum value. And finally, we have the constraints that set bounds on the voltage angles and establish the reference bus. Okay, so now let's move on to the real-time hardware in the loop simulation setup that we have designed to test and validate optimization-based controls, the RTO lab, developed at the Electrical Engineering Department of UC3M. We have designed this simulation framework to emulate the overall operation of the grid, integrating control algorithms ranging from high-level operational strategies based on optimization to the low-level controls of each asset in the grid. To achieve this, RTO Lab integrates a real-time digital simulator together with a PC, a PLC, and an industrial computer. Thus, the architecture of RTO Lab comprises three levels, each hosted on these devices. Okay, so um, let's start with the top level layer, the real-time optimization interface, which is implemented on the industrial computer and executes the optimization algorithm in real time to generate the optimal set points. It has been programmed in Python using the Piomo optimization modeling language. Okay, so once the set points have been generated by the top level layer, they are transmitted to the intermediate level hosted on the PLC, which manages and distributes the set points among the different generators of the system. And finally, the RTDS together with the PC constitutes the bottom level, where the system model operates in real time. And using the RSCAD simulation environment of the RTDS, the grid and all system assets, including their controllers, have been modeled. And in this setup, the system controllers receive the set points from the intermediate layer in real time and respond dynamically to make the necessary adjustments to follow the set points and respond to changing grid conditions. These grid conditions are given by load and renewable generation profiles, which are continuously fed into the real-time simulation model from the PC based on data provided by the system operation. And communication between the different layers is carried out using the Modbus protocol. Okay, so um, once the overall structure of the tool has been presented, let's continue with its implementation for the control proposed in this paper. As shown, on the one hand, the scheduled active power set points for the dispatchable generators are loaded on a hourly basis, as they are the result of the unit commitment or market clearing performed the previous day. But in contrast, the load and renewable generation forecast are updated at each optimization interval, incorporating the most recent available data. Then, at each interval, the optimization problem is solved using the EPOP solver, and the resulting voltage or reactive power set points, along with the updated active power set points from redispatch, are transmitted to the system. Okay. As you can see, we are applying our formulation to the interconnected grid of the islands Fuerteventura and Lanzarote, which functions together as an isolated grid. This grid is characterized by two conventional power plants at buses 13 and 14 on the slide, as well as by distributed wind and PV resources, which we have modeled in aggregated form. Additionally, we have integrated a battery, which is not currently part of the real system, but provides the grid with suitable characteristics to explore management strategies. This system has been modeled in the RTDS using sixth order synchronous machine models for the conventional power plants. And for the generation connected through inverters, we have implemented voltage source converters. Okay, so let's go through the experimental case studies carried out in the RTO lab. These tests were run in real time over a 2-hour period. And for comparison purposes, a base case was executed first, representing the current operation of power systems. In this case, generators receive the scheduled active power set points on a hourly basis as determined by the scheduling mechanisms performed the day before. And now optimization is applied. So generator follows fixed voltage or reactive power set points. And then the proposed strategy was used to execute 4 cases with the optimization window varying in 5, 15, 30, and 60-minute intervals. In these cases, at each optimization interval, generators receive the updated active power set points resulting from the redispatch, along with the optimized voltage and reactive power set points. As in real power systems, the accuracy of the forecast improves as the optimization interval shortens. Okay, so now let's present the results, and let's begin by analyzing the findings in terms of active power losses. As shown, the power losses in the system for the base case, represented by the green line in the graph, are significantly reduced when the optimization strategy is applied. In this case study, the shortest optimization interval of 5 minutes led to the most significant loss reduction, namely over 18% compared to the base case. Nevertheless, the differences among the various optimization intervals remain moderate. And another important aspect to evaluate is whether the system performs adequately when receiving the optimized set points. And this was verified by analyzing the electrical variables of the system. And as you can see, the voltage profiles and the reactive power outputs demonstrate that the variables remain within the defined limits and exhibit acceptable dynamics. And finally, another key variable analyzed in the results is the active power output of the synchronous generator in Lanzarote. Since this generator had the lowest redispatch cost, it was the only dispatchable unit whose set point was modified, represented by the solid black line, compared to the schedule one, showed as the orange dash line. And additionally, in this system, this generator is equipped with a secondary control loop, making it the unit responsible for maintaining the power balance. So it compensates for deviations between the forecasts and actual values by adjusting its output, shown as the solid blue line. And as you can see, as forecast accuracy improves with shorter optimization intervals, the optimized set point increasingly converges with the generator's actual output, reducing then the effort required from secondary regulation. So let me now conclude the presentation with a summary of the key findings and some notes on future work. This paper proposes a centralized real-time reactive power management strategy based on a modified optimal power flow formulation. The goal is to minimize system losses and redispatch costs while ensuring that all steady-state constraints are respected. The strategy was tested on the Lanzarote Fuerteventura power system using the RTO lab, and results indicate that shorter optimization intervals lead to improved performance as more frequent updates enable the system to operate closer to its optimal point, thereby reducing losses and the burden on secondary regulation. And also the differences among optimized cases are moderate. The improvement over the non-optimized base case is clearly significant. And finally, the successful implementation in RTO Lab demonstrates the feasibility of applying this strategy in real-world systems and hardware with satisfactory convergence and dynamic behavior. And as for future work, we plan to incorporate stability constraints, which will increase the computational complexity of the problem, making its assessment under realistic conditions a key aspect. And with that, I am happy to conclude my presentation. Thank you all for your attention, and I look forward to any comments you may have.
Thank you very much for your presentation. I have a question. I can see that in your model you introduce a battery. Do you mean that this storage is necessary to improve the control strategy? of the Lanzarote Fuerteventura system?
Well, for this case study particularly, this asset does not improve the performance because we are now just. Carlos, can you mute your micro because I'm hearing myself and can you mute your micro, please?
Yes, sorry.
Okay, thank you. In this case study, the battery does not improve the performance of the algorithm as we are not managing energy. Let's say that we are just optimizing the real-time sharing of reactive power. But if we think in, let's say, an energy management system, of course, the battery would have to be taken into account. And of course, if we consider for example, the inertia behavior and the voltage control capabilities that these kind of assets can provide, of course, this could improve the behavior of the whole system. But let's say that for this algorithm, it's just an asset that follows the optimized reactive power set points.
Okay, thank you very much. Someone has one question, something? No? Okay, thank you very much. We have no more questions.
You're welcome.
And then would you like to pass to the last. The last presentation is for Matilde Santos and Fernando Herrera. Is online. I think they are not here. Is Matilde Santos or Fernando Herrera ready? No. Then if they are not here, we just finish with this session. We have all the presentation. Thank you very much for everyone to be here.
Thank you, everyone. Bye.
Bye-bye. And that's it. Es extraño porque Matilde estaba y luego me dijo, dice, va a presentarlo Fernando Herrera.
Well, good afternoon, everybody. My name is Luis Lopez, and I am from Concordia University in Montreal, Canada. And then I'm going to be chairing this section, right? So this is an online session, not very common, but I'm glad that you guys are here to work with us, okay? So we have 5 papers. Paper number 1, the author has not yet connected, right? Might be having some sort of connection problems. And then I suggest that we go with paper number 2, okay? So just to remind you that according to the guidelines from the organization, you guys have 15 minutes for the presentation, okay? Including 12 for the presentation and 3 for questions, right? So at 10 minutes, I will kind of give you a heads up so that you can conclude the presentation in 12 minutes. And then we have these 3 minutes of questions, right? So if you guys can also participate in the questioning, it would be great so that we can collaborate and participate, okay? Very well, so having said that, let's start with paper number 2. So the title of the paper is Design of a Control Strategy. DC electronic converted to supply virtual inertia for a renewable energy source connected to the unbalanced electric grid. Okay, so I believe that Mr. Marcos Galledo Colado will be making the presentation. Marcos, please go ahead and start the presentation. Thank you. Marcos?
Okay, please. Thank you. Good morning, everyone, and thank you for joining to this session. My name is Marcos Gallegos. I'm a master student in Pontificia Universidad Católica del Perú. Please, can turn off your microphone? I can hear you.
Mute the microphone while you are not.
Thank you. Good morning, everyone. My name is Marcos Gallegos. I'm a master student in Pontificia Universidad Católica del Perú. Today, I'll be presenting the design of a control strategy for a 3-phase DC-AC electronic converter to supply virtual inertia from a renewable energy source connected to unbalanced electrical grid. ¿Cómo avanzo acá? I'm trying to next page. Please give me a minute. Please give me a minute and I am having a problem, technical problem.
David, do you have something to suggest? No.
Please give me a minute to solve my problems.
Sure.
I have some problems with the presentation. Okay, I will start. Can you hear me, please?
Yes.
Thank you. Thank you for all. I will start. Good morning, everyone. My name is Marco Gallegos, and I'm a student master student of Pontificia Universidad Católica del Perú. Today, I'll be presenting the design of a control strategy for a three-phase DC-AC electronic converter to supply virtual inertia from a renewable energy source connected to unbalanced electrical grids. Introduction. The tables of contents. I will start with the introduction, then the amplitude and phase voltage unbalance, the control strategy, then describe the design of the system control, the operation of DC-AC converter under amplitude and phase unbalanced conditions, the conclusions, and in the end, a proposed futures works. In this section, I will talk about the electricity sector. The different economic sectors, such as building, industry, transport, demand energy with security and reliability. Today, the renewable energy had 34% in 2025 and expand to 45% in 2030. Different economic sectors are interesting to produce new source of energy. This is the reason why the industrial sector is building its generations, plans to self-consumption. The problem of stability and renewable energy resource. In this picture, we can see the dynamic response of the frequency drop due to the increase of grid load. We use two fundamental parameters. The first is the lowest frequency away from the nominal frequency. The second is the rate of change of frequency measured at the beginning of the transient. We can see the diagram, the block diagram representation of the swing equations is the base of the inertia calculation. And obviously, we can see the natural behavior of the generators. When we increase the power, the mechanical speed decrease and the frequency. In this section, I will present the amplitude and phase voltage unbalance in three-phase systems. International standards such as IEC and ICREPQ define the limits for voltage imbalance and define the voltage imbalance factor that is present in this equation. For analysis, the unbalanced three-phase network was modeled with voltage variation as shown in this table. And in this image, we can see the representation of the variations with increase of 5% in the phase up in magnitude and decrease of 5% in the magnitude of phase B. The variation in the phase degree in phases C and B. In this page, we can see the screenshot of the software simulation with the modeling performed using different blocks. The first to amplitude imbalance, and the second to the phase imbalance. When applying the DQ0 transformation to the unbalanced voltage system, oscillation with the amplitude frequency equal to twist of the nominal are observed. We can see in this image the increase of the value of these oscillations. When we increase the imbalance, we can see the increase of these oscillations. Obviously, this was studied by different papers, and this, in essence, this is the description of the problem: the appearance of the second harmonic that distorts the frequency measured in the network under voltage imbalance conditions. When we use the fast Fourier transform, the problem under study is clearly observed. Control strategy. The objective of the CAC converter control is to regulate the bus voltage in the DC bus, maintaining the balance between the power supplied by the resource, renewable energy source, and the electrical grid. The control strategy is based in the implementation of a PLL with a controller that allows tracking the phase and the frequency of the voltage wave in the power plant. Supply network and at the same time limit the velocity. In other words, implement a slope controller that allows to follow the voltage variations in the DC bus. It also includes the tuning of the PLL control system and the design of that cascade control. The current control loop, the voltage control loop, working together with the frequency control loop. The PLL control loop strategy, the PI controller designed for the PLL was developed using the symmetric optimum method with different cutoff frequencies. We observe change of the behavior of the systems. As the cutoff frequency is varied, the controller acts as a filter that limits the distortion generated by the imbalance, obtaining the best results at a cutoff frequency of 10 Hz. This is represented by the red line in this graphic. This picture presents the modeling using software, and the phase estimation controller is intentionally slow so that it can adjust the speed of the voltage loop. In this case, we can see 3 cycles to reach the true phase value. Current control loop. In this part, we can observe the current control loop with a diagram block and the modeling software and the response we obtain in simulations. The current control and designs was carried out by evaluating the response to unit step, selecting a cutoff frequency of 800 Hz. Is represented by the red line in this graphic. Voltage control loop. In this picture, we can see the block diagram of the voltage control loop transfer function is typical in all the papers, state of art, and modeling the software. And we can see the response with the time step with one step of 10 to 16 amps. The description of the inertial loop is very simple because it's a proportional. In this table, we can present the results of the parameters of the different controllers that implement in this study. In addition to this, the design filter stopping band was considered by the improved our results. In this table, we can see the parameters of the design filter with three blocks with the different cutoff frequencies and the effects of the rejection filter and the reference current. We can see the difference with and without filter. The improvement of the PLL in frequency tracking in unbalanced condition with filter is evident by the reduce of the flicker by 0.33 Hertz to 0.003 Hertz. The next part present the operation of the DC-AC converter under amplitude and phase unbalanced conditions. Operation of the DC-AC converter under amplitude and balance condition. In this section, analyze the behavior of the control system for the injection of virtual inertia in the phase of frequency variations under condition of voltage unbalance in supply network. The analysis was performed considering frequency drop of 0.3 Hertz with rate of change of frequency of 3 Hertz by second at time 0.8 seconds. This we can see in this picture and the response of the PLL in the tracking of frequency. In the next image, we can see the discharge of the bus DC of the capacitor with the variation of the voltage on the DC bus. And in the next picture, we can see the results, the obtained results with the active power. We consider the active power in two parts, average power and avalanche power. We can see that the behavior of the system present a good performance with average power of 900 watts. The next section presents the operation of the DC-AC converter results obtained in the simulation carried out using software. This first image shows the profile of the currents. We can see the distortion of the current on phase A. It's evident that we can improve this performance. And this next image present the reduced distortion present with the use of a filter stopping band. With the implementation of the filter, the balance of the three-phase current injected into the network is partially improved, especially in phase A, which was totally distortion without the filter. In the next image, we can see the response of the frequency. We can see the response of the tracking of frequency by the PLL at the time 0.5 seconds. The fast response, relative fast response, because the PLL is slowly. And the variations in front of imbalance and variation of frequency in the grid. The active power supply by the system is described in this image, and the virtual inertia control system responds under phase and balance conditions. Conclusion. This paper presents the design of a control strategy for a three-phase DC-AC electronic converter based on the use of PLL as a phase and frequency tracking element applied to unbalanced electrical system in order to provide virtual inertia. The main contribution in this design is a low complexity control system based on tuning of the PLL current, voltage, and virtual inertia controller to optimize its operation in unbalanced networks. The controller designed for the PLL acts as a second harmonic filter, facilitating the tracking of the frequency signal and allowing the operation of the control system under voltage and balance conditions. Furthermore, the proposed second harmonic filter improves the stabilization of the reference currents in the current loop, allowing to further improve the waveform and balance of the current supply to the grid. Thank you for your attention and attention by your questions.
Thank you very much for your presentation, Marcos. So to people online, do you have any questions for Marcos? Or people in the room, would someone come up with a question for Marcos? So if you have a question, please come to the podium here, right? So to be close to the microphone. No? Marcos, I have a question for you. Can you go to slide number 8, please?
Okay. Okay.
Right. So, from what I know in terms of this inertia, right, virtual inertia, it will be changing the amount of injected power, right, based on the frequency of the grades. Is that correct?
Yes, okay.
Right. Now, if you have to change this amount of power you're injecting, but then you have a PV source there. You don't have a storage element there. Okay. So I mean, I believe that to be able to supply extra power when the grid frequency decreases, if you have to be operating the PV below the maximum power point. Is that so?
Okay. Please, this system works, we provide this, the performance of this technical propose by different levels of power supply. The results is according to the dimension of the system. If we increase the capacity of the DC bus, we increase the power supply to the network. And we had limitations with the magnitude that imbalance in the system.
Okay. Again, sorry for the...
If you can explain more about your question.
Right, yeah. So my question had to do with this virtual power generation there. Because the moment that the grid decreases the frequency and you have to supply more power, okay? So if you're operating your PV panel at the maximum power points, you cannot go beyond that. You cannot supply more power to the grids, okay? So understand that if the grades frequency goes up, then you can decrease the amount of power you inject, active power. But if the frequency decreases and you are operating at the maximum power point, then you have no spare power to inject into the grids as if your source, right, or as your PV had inertia characteristic. Okay. But anyway, if you wish, send me a message, Luis. So you will see my contact there, and then we can go into more discussion this. Very interesting topic. So anyway, thank you so much, Marcus, for your presentation. We still have time for more questions from the audience, if someone has a question. Good. So thank you, David. I see that you gave some hands up for the Marcus. So thank you so much, Marcus. Very good job. Juan Javier too. Thank you, Juan. All right, so I guess that we can now go for our second paper. So this is a paper from Feng Hu. Feng, are you with us now?
Yes.
Good.
Okay.
So, if you can start your presentation, this would be much appreciated. Okay? Thank you very much.
Thank you. Thank you very much. Can you see it?
Yes.
Okay. Hello, everyone. I'm Feng Hou from the School of Informational Energy at Southwest University of Science and Technology in Mianyang, China. Today, I will be presenting our paper entitled Optimize Inter-Real-Time Simulator Communication out the Transmission Line Delay Variety. I will explain from the above aspects. Firstly, the background and motivation. The large-scale integration of renewables and power electric reels safety and stability demands, necessitating higher computation power and smaller time steps in electric transit and real-time simulation, which are met through parallel computing via distributed paraments, transmission line decoupling, and American-level FPGA-based data exchange. Traditional one-time step exchange latency watches FPGA resource and hinders scalability, whereas matching its link's communication latency to its actual progression delay enables linear higher throughput FPGA-based data exchange with full simulation fidelity. Below is the optimization method. The Virgin line model is commonly used in the electromagic transit simulation for the long-distance transmission line with distributed parameter, as illustrated in Figure 1. By using the Virgin pi model's inherent progression delay to exchange historic boundaries whereas affected by one more time steps. Each sublet can be solved independently in parallel without loss of accuracy. By classifying data into low, medium, high latency based on link propagation delays and using 3 HLS generated pre-configured FPGA modules to exchange streams in parallel without per-packet headers. We match communication latency to physical delay, dramatic reducing resource use and boosting throughput with full accuracy. The above modules can be synthesized as IP card shows in Figure 2. For each simulation step, the FPGA switch demultiplies incoming data into low, medium, high latency streams, processing them in parallel through the dedicated methods, and receives both and forwards the packets, allowing out of order exchange without loss of fidelity. Although using three switch modules, the overall design resource can be lower due to the resource optimization. Below is the case study and the results. We have built 4 units of Dongju. The real-time simulator achieved the integration simulation of 20 sets of 1 triple OE 3-9 nodes, power grids, and 100 wind triples through a simulation platform interconnected by FPGA fiber optic switches. Interconnects by the switch using the FPGA as shown in Figure 3. The simulation step size of the system in 10 US, and each step size requires the exchange of 900 bit varieties. 115 variables are exchanged between the power grids through 50 transmission lines, and 300 control variables are exchanged between the wind turbine and the power grid. All components and interconnect through the bridging transmission line model, as shown in Figure 4. Through FPGA large resource, the construction lookup tables were reduced by 14.7%, and triggers were reduced by 14.8%. To demonstrate that the proposed method does not introduce errors at the 2-second time points, a fault occurs on the grid side near the wind turbine, which lasts for 0.1 seconds. The transient response of a wind turbine system includes DC voltage, active power, reactive power, and instantaneous current, as shown in Figure 5 and 6. The results match well before and after obtaining the proposed optimization method. Below is the conclusion. Leverage Bayesian model training will designed to optimize inter-simulator communication, achieve 48.8% FPGA resource reduction without loss of simulation accuracy. Demonstrate on 4 race-time simulator with 20 IEEE 39 bus systems and 100 wind turbines. This method increases data throughput under the same hardware and is applicable to multi-machines electromagnetic transit studies. Thank you for your attention.
Thank you very much for your presentation, Feng Hu. So, any questions from the attendants there online? So, any questions from the audience in the room? Feng Hu, I have a quick question for you. Can you go to those waveforms that you presented there? I guess maybe it was one before the last slide for the conclusion.
Okay. This.
Right. Yes. Yes. So, well, looking at the screen, it's not easy to see the difference between the two cases, right? The benefit that you get from this proposed algorithm, is it in terms of the waveforms that they are more accurate, or it's that you get the same or similar accuracy, but with lower work from the FPGA?
Give some minutes. I will question. Okay.
Because in the conclusions there, you mentioned something about the FPGA working less. So it seems that you get similar results.
Oh, sorry. My English speaking and listening skills aren't very strong, so I missed a part of your question. Would you mind email me the details? I'll be happy to send you a detailed response as soon as possible. Oh, I'm sorry.
All right, I will do that for sure. Thank you very much.
Thank you.
Right, so now, thank you, David. So now let's go for a presentation of paper number 3. Okay. So paper number 3 is Alberto. Are you with us, Alberto?
Yes.
Excellent.
Let's open the camera. Okay, now you can see me. I'm gonna share the presentation.
You can see you. Nice time.
Thank you. Here is the presentation. I'm gonna put it in full screen. Can you see it properly?
Yes, very well. Please proceed with your presentation, Alberto.
Thank you. Thank you very much. Good evening, ladies and gentlemen. My name is Alberto Monteroso, and I'm going to talk about the following topic: experimental analysis and modeling of an AIM electrolyzer. The contents of this presentation are stated below. First, an introduction and the main objectives of this work are to be presented. Next, the characterization of an AIM electrolyzer is displayed, followed by the methodology and model description. Finally, we'll present some results of this modeling, followed by the conclusion and the references of this work. In order to kick off, we're going to introduce the main technologies that are used in green hydrogen generation. The most extended green hydrogen technology by far is the alkaline electrolysis. It was the first to be invented, and its good ratings of efficiency and affordability have set a good standard in the industry at high power levels. However, With the increasing deployment of renewable energies, more flexible solutions are beginning to be needed. In this regard, proton exchange membrane is a new technology that excels in dynamic response and compatibility with renewable energy sources. In the same page, but as a younger technology, anion exchange membrane with a 6 to 7 TRL provides a cost-effective solution between alkaline and PEM while maintaining closer characteristics to those of PEM. On the contrary, AM research is very limited, mainly focused on stack materials and at a pure chemical level. The objective of this work is the characterization of an ion electrolyzer stack by means of a multi-objective criteria: startup and operation, polarization curves, stationary test, and dynamic performance under photovoltaic renewable energy sources. This belongs to the ion electrolyzer characterization stage. In addition, we have developed an experimentally validated AML electrochemical model, and some results from this model are to be presented. First, this is the electrolyzer unit present in our laboratory at the National Institute of Aerospace Technology in Spain. It is a recent commercial electrolyzer from the brand Enafter, model EL 4.1. This is going to be the experimental setup of this work. Among the most interesting parameters, we can highlight a nominal hydrogen production of 8.3 normal liters per minute, a maximum output pressure of 35 bars, a maximum operated power of 2.4 kilowatts, and a water consumption of 0.4 liters per hour. The studies we have conducted in this experimental setup are listed below. First, the startup can be made in two different scenarios. First, a cold start, which takes about 20 minutes, and a warm start that consists of a 45-minute preheat process to reach at least 40 to 45 degrees Celsius of temperature. And then we switch the machine on and perform the startup process, which consists of 8 minutes. This last scenario is the preferred one, as it prolongs the lifespan of the unit. The temperature set point of 55 Celsius is the normal operating point at nominal power and is fully controlled by a PID controller. The second test we have performed is a polarization curve to analyze the steady state, stepwise increments in current with an amplitude of 0.5 amps in the range from 32 to 53 amps, which are the full operational range of the electrolyzer, with a resting time of 3 minutes per step. Additionally, we have performed long-term stationary tests, which consist of the AM unit operating for 5 hours at constant power levels, at 60% to 100% in 10% increments. Finally, we are going to test the dynamic performance with a photovoltaic energy scenario under a demanding winter cloudy profile. The methodology followed by the model is a semi-empiric, nonlinear parametric. The input parameters of this model are the stack current and what we call additional physical constants, which are physical and chemical properties specifically tailored for the IM electrolysis. As for the outputs of the model, we can predict the stack voltage, the hydrogen flow, and the efficiency of the stack. In the right part of the slide, you can see an overview of the IM electrochemical model implemented in the MATLAB Simulink software. A brief lookup into the model insights revealed that the cell voltage of a generalized electrolyzer model consists of the sum of the following terms, which are the reversible potential, the activation potential, the ohmic potential, and the ion voltage, ionic. Here you can see clearly the nonlinear nature of the electrochemical model. And in the right side, we can see the calculations for the hydrogen flow and the efficiency of the stack, considering the lower heating value of the hydrogen molecule. We have added a degradation compensation parameter that is defined as a function of cell voltage and hours of operation. As a result, we present both the operational tests in blue versus the simulation obtained by the model all in the same slide. This test belongs to the most basic one, which is the polarization curve. And we can see that the general envelope of the electrochemical process has been well captured, with some interesting parameters of the model on the right side. We can see that the 8.3 normal liters per minute stated by the manufacturer is something that can relate to experimental results as well. And the efficiency ranges from 62.5 in the best scenario to, well, in the worst scenario, to 65%. The peak efficiency is reached at the lower power level. The next test is the stationary long-term at nominal power. We can see that even the transients are well captured with a brief deviation caused by the long-term electrochemical equilibrium. Finally, the most challenging test is the dynamic one, which is a topic not widely stated in the literature, especially for IM electrolysis, which consists of a winter solar profile on a highly transient scenario. We can see that this electrochemical model performs very well, even under dynamic scenarios, with response time of 45 to 15 seconds. So it is able to react to power changes in under a minute, which is a very good asset. Finally, the error metrics of the models are presented. The IM model with the classical equations is represented in the blue bars, and the degradation compensation model, which is based on the former one, is represented with orange color. We can see that the mean average error has dropped from 0.6 to 0.2, 0.228, and the root mean square error has also followed the same fashion. As for the mean bias deviation, which expresses how much is the model over predicting or under predicting, is actually the best metric that has improved. We had a deviation from minus 0.6 volts, and we have actually corrected it to a little over 0.2 volts, which is fairly more acceptable. As a conclusion, we can see that IM electrolysis is in transition from prototype to a small-scale commercial stage. It offers a good dynamic performance and adaptability to fluctuating renewable power sources. The IM model presents a MI of 0.28 volts, a root mean square error of 0.35, and a mean bias deviation of plus 0.22%. As future work, we are trying to improve the transient response, a call for further more reliable stack degradation analysis, and scientific effort on larger data sets. These are the references of the work, as well as the acknowledgements to the project OPAL H2, funded by the European Union Next Generation, the project ODL H2, funded by the Andalusian government, as well as the project AIRE, funded by the European Regional Development Fund. With all things said, thank you very much for your attention, and I will be pleased to answer your questions.
Thank you very much, Alberto. So first, let's start with people online. Any questions for Alberto? So, any questions in the room here for Alberto? Alberto, I happen to be working on a similar topic, right? So I'm very much interested on what we're doing. So the tests that you described in slide number 5. Okay?
Slide number 5.
Yes, so for the characterization of the electrolyzers. So, I mean, first question is this. So, I mean, is it something that is a standard for the characterization of electrolyzers, or is this something that you conceived, you proposed?
Very interesting question. We have followed the JRC 2018 normative, which is normative from the European Union regarding the polarization curves and operational characterization of electrolyzer stacks in general, regardless of the technology. And it is a document that can be downloaded, and for each specific case of technologies, I think the alkaline, PEM, and of course IM are the three that are included. They have like specific parameters, and yeah, we have actually inspired in this kind of test.
So my last question is on slide number 8. So can you go to slide number 8, please? It's there. Okay, yes, so I mean, I'm still having problems unmuting and muting myself. So, last question, Alberto. I apologize for that. So, if you go to slide number 8, please.
Yes.
Yeah, for the experimental results, I guess, huh?
Yes, the first slide of results.
Yes, number 8. Because we see some, in the blue waveform, there was a blue waveform there with some sort of spikes.
Yes.
Slide number 8. So can you share with us slide number 8?
Can you see the slide?
Yeah, we see, yes, now.
Okay.
Right.
Okay.
Now they're good.
Sorry?
Yeah, now this is the slide I was talking about. So when you look at this difference between the experimental and simulated voltages there, right? Any reasons for those transients that you see there? Like the red curve is kind of standards, right? But when you go to the blue, we have some sort of transitions now and then. So would you be able to explain why we have those transitions?
Yes, of course. I'm glad you have brought this up because it reveals a fundamental aspect, property of this system. The equation modeling we have proposed has some assumptions, and this behavior has not been considered in the model. So we can say that the model is generalization of the real system. Those spikes you can see in the true blue curve are related to the automatic water recharging of the system. We have an electrolyzer that is consuming water at a rate of 0.4 liters per hour, and every 30 minutes or so those 400 milliliters are automatically introduced into the electrolyzer internal tank from a water tank. So we can see that this is actually representing temperature. So we have a process going on at 55 Celsius. If we actually introduce water at room temperature, that can be 25 Celsius, the thermical equilibrium is disrupted for a brief period of time, and it traduces in a voltage spike because the electrolyzer is working for a short time with a lower temperature, and that is a mini stress to the system.
All right, thank you very much, Alberto. It kind of reminded me of a fuel cell that we have, an open cathode fuel cell, and there is a phenomenon they call this hydrogen purge in the fuel cell. Okay, so I mean, that's something that came to my mind. So again, any questions from the audience? If not, let's go for the next slides. Next presenter. Very well. Thank you, David. Thank you, Alberto.
Thank you, Carlos.
Thank you, Juan, for your hands up to Alberto. Very well. Great. So now we have David. David for his last presentation of the session, right? So David, the floor is yours.
Okay, good afternoon to everybody. My name is David Carrasco Gonzalez. I am a PhD student from the University of Cadiz. And I'm in this session, and I'm going to present the paper called Dynamic Energy Management System for Optimal Energy Dispatch in a Microgrid Cluster. This is the index of this presentation. Then the presentation starts with an introduction of the work. Nowadays, renewable energy sources have become significant owing to the international commitment to reduce greenhouse gas emissions. Additionally, there has been an exponential increment in the electric demand. In this situation, conventional grids are tending to transform to small, smart, and independent grids denominated as microgrids. The microgrids are constituted by renewable energy sources, energy storage system, and electric loads, and they can be connected to a local grid. This generates two different modes. The first mode is the islanded mode, where the energy generated can only be stored and consumed. And another mode is the grid connected mode, where the local grid can solve the different power mismatches generated in the microgrid. In this situation, several microgrids can be connected to constitute a microgrid cluster. To manage the microgrid cluster, energy management systems are usually used. Nowadays, the use of intelligent energy management systems, such as sequence quadratic programming algorithms, are becoming significant owing to their benefits. Then this paper presents a new centralized and dynamic SQP energy management system for a microgrid cluster. This slide presents the microgrid cluster configuration that is constituted by two microgrids, an AC microgrid and a DC microgrid interconnected to a local grid. The AC microgrid is constituted by PV panel, a battery bank, and three-phase loads. Otherwise, the DC microgrid is constituted by a wind turbine generator, an ultracapacitor, DC loads, and a hydrogen system composed of a fuel cell and an electrolyzer. As you can see in the figure, the PV panels, the battery, and the DC microgrid use a voltage source inverter to transform DC power into AC power using cascade control loops. Additionally, the wind turbine generator uses a uncontrolled rectifier to transfer AC power into DC power. Regarding to other local controls, the PV panel uses the maximum power point tracking strategy, and the wind turbine generator control its speed to optimize their power generation owing to the variant solar radiation and wind speed. Regarding to the energy storage system, PI controllers are used to adjust the active power exchange on this device. And finally, the loads and the local grid don't require any action control, although the load uses circuit breakers to connect and disconnect them into the microgrid. To manage the microgrid cluster, a dynamic centralized optimal energy management system is developed in this work. This energy management system is based on the next premise. The PV and the wind turbine generator contribute to a single generation pool. And additionally, the load of each microgrid contributes to a single consumption pool. When there is a power mismatch in the microgrid cluster, the energy storage system covers the power mismatch to avoid to exchange energy with the local grid. And this is the main objective of this energy management system, to avoid to use the local grid to exchange energy. The use of the energy storage system is the next. The battery is restricted by its state of charge to maintain a safe operation. The hydrogen systems support the battery, but they have a minimum power generation or consumption regime to avoid disconnect this device into their respective micros. Finally, the ultracapacitor, owing to its fast dynamic, cover the transitory power mismatches that cannot be supported by the other energy storage system. Then these equations are the implementing the algorithms. And first, you can see the objective function that mainly calculate the difference among the generated power, demanded power, and as you can see in the left side of the equation, the energy storage system covers the power mismatch generation. This algorithm is limited by the net power constraint of the energy storage system. In the case of the battery, it is limited by its state of charge, as I mentioned before, and additionally to the maximum power output. In the case of the hydrogen system, they are limited among the minimum power generation or consumption regime and their maximum power output. Finally, the power reference of the ultracapacitor is calculated among the different is calculated as the difference among the actual set point of the energy storage system and the current value. Then in this situation, the second simulation is executed in Simulink to test the behavior of the microcluster and the energy management system under different working conditions, such as incidence, variant solar radiation, wind speeds, and additionally the loads are connected and disconnected at different times in server. As you can see on the left side of the slide, figure 2 presents the generated and demanded power and the power exchange with the local grid. As you can see the figure, the generated power and the demanded power profiles are modified when the input parameters are changes in the simulation. One point, as you can see in the figure, the fluctuation of the wind turbine generator and the DC load demand profile are generated owing to the fluctuation on the DC bus voltage. This situation is not generated in the EC microgrid because the local grid maintains constant the grid in this microgrid. Finally, the local grid participates covering the power mismatches that cannot be supported by the energy storage system. And when the power balance is reached, it's sent to zero. As you can see in the result, the power sharing with the local grids maintains minimal respecting other signals, and this complies with the objectives fixed in the energy management system. Figure 3 presents the difference among the generated power and the demanded power. As you can see in the figure, when the generation is higher than the demand in two intervals among 0 and 2.5 seconds, and in the second interval among 3.5 and 5 seconds. In the rest of the simulation, the consumption is higher than the demand. In this slide, figure 4% the active power chain of the energy storage system. As you can see, all the devices follow their respective references perfectly. And additionally, when the generation is higher than the demand, the battery and the electrolyzer consume the energy. Meanwhile, the fuel cell maintain the minimum generation regime. In the opposite side, when consumption is higher than the generation, the fuel cell and the battery supply energy. Meanwhile, the electrolyzer is maintained in the minimum generation regime. Finally, neutral capacitor cover the transient power mismatch that cannot be supported by the other energy storage system. Finally, figure 5 presents the DC bus voltage that is perfectly controlled around 1100 volts. The changes generated in this figure is produced by changes in the device that constitute the DC microgrid by different changes of input parameters or in the energy storage system. And the control of this parameter is crucial for a stable operation in this microgrid. With this result, we can conclude that the microgrid cluster and the local control has an adequate performance. The centralized dynamic optimal energy management system has a successful operation based on the premise fees in this work. And all the system has a proper response and different working conditions. And the main objective of the EMS reach minimum power exchange with the local grid is reached. We had in the result a minimum power exchange with the local grid. Thank you for your attention.
Thank you very much, David. So, any questions from the colleagues online for David? No questions? So, from the room, no questions. All right. So, David, I have a few questions for you. Okay. So, if you go to slide number 8, figure number 5, I guess. Right. So, if you look at figure number 5, yes. So if you look at these DC bus voltage profile there are some like high peaks there, like most 1,200 volts.
Yes.
So I mean, you know, if you kind of relax some of those limitations or constraints that you used for the fuel cell and so on, right? So would you be able to reduce this peak voltage there, these transients? So what could you do to make this like lower, to prevent this high peak voltage there?
Okay, we can try to improve in future work the synchronization of the PI controller, for example, to reduce the for the current value follow the set point better than in the actual state, for example. I think you have mute.
Right, again, I apologize for that. Yeah, so I mean, what I was saying is that, you know, if you look at this power of the ultra cap, right? So there's a reference value and then the actual value. Reference is the red curve, blue is the actual one, right? So I mean, we can see that sometimes, you know, some of those values cannot be tracked. So maybe if you prevent some of those limitations there, you know, during some cases, then you would be able to keep this voltage profile better behaved, you know?
Yes. Yes.
But wait, I understand that this is an ongoing project, right? And then you have some new ideas, and I hope that you can bring even better results for us next time.
Yes. Thank you.
All right. So thank you very much, David. Well, this was the paper number 5 of 5 papers. Unfortunately, thank you, Juan. Unfortunately, and Alberto, right. So unfortunately, we did not have one of the papers, but we had more time for discussions of these 4 papers. right? So thank you so much, guys, and I hope that you enjoyed the conference. Have a great day, and hope to see you soon next time and in person.
Okay.
All right?
Thank you.
Thank you, guys. Have a good day. Bye-bye. Guess that's